Hello and welcome to this movie about magnetic materials. The mathematics of them is very similar to that of dielectrics, but the magnetic B field is divided by the main constant mu0 to make the magnetic H field instead of being multiplied. The new magnetic field vector H is not the total magnetic field, but only the externally driven magnetic field created by the currents in the solenoid. I decided to define vector H subscript T to be equal to the total magnetic field created by the solenoid and the magnetic material in the core of the solenoid, just so that I could more easily follow the math. Here is an air-cored solenoid. There is no magnetic material in it to contribute to the total magnetic field, so the total magnetic field HT is equal to H. Here is a cross-section of this solenoid with these vectors inside it. Here is the relation between these vectors. H is just B0 multiplied by a constant, so is just another way of writing B0. Here is the same solenoid, but with an iron core inserted. The core may be just a suspension of iron particles in a resin. This could cause the induced magnetic field in the core to be about 1.5 times larger than the magnetic field in the air-cored solenoid. Here is a cross-section of this solenoid. Here is how these magnetic field vectors relate to each other. Bt, the total magnetic B field, is equal to the sum of the magnetic field of the solenoid B0, or BH, plus the magnetic B field induced in the material, called Bm. Notice that the induced magnetic B field is in the same direction as the solenoid-driven external magnetic B field, so as to increase the new total magnetic B field. This is in contrast to dielectrics, whose induced field opposes the external field. Here are the magnetic H field vectors. HT is the total magnetic field. I've inserted it so as to make the math easier to follow. The equation written below relates these three variables together. These magnetic B fields and H fields correspond to each other and are equivalent to each other. BH is equivalent to H, BM is equivalent to M, and BT is equivalent to HT, because BH is equal to the quantity mu0 multiplied by H, so H and BH are just different ways of writing the same quantity. Here is a list of the equations relating the magnetic quantities. There are two variables called chi m and kappa m, which are analogous to their dielectric versions or counterparts, chi e and kappa e, being properties of the materials. These equations may be used to derive other new equations or to derive each other. Here is an example of how to derive this main equation written in textbooks from these other three definition equations. Notice that it is only algebra without fancy integral equations. This is an example of how to find a relationship between chi m and kappa m, which have a very simple relationship. This is an example of how to relate the magnetic B fields to each other. Here is an example of how to find magnetic field vectors without knowing anything about the externally driven field BH or H. And here is another example of this. Here is a cross-section of a solenoid with a paramagnetic core. The induced field is extremely small compared to the externally driven field, and in the same direction, so as to make it a bit larger. Here is a solenoid with a diamagnetic core. The induced field is small, but now in the opposite direction to the externally driven field. This induced field vector is drawn in a different color so as to make it easier to see. Here is a solenoid with a ferromagnetic core, which induced a field in the same direction as the externally driven field, and much larger than it. Chi-M changes a lot in this material due to hysteresis, but for the practical study of it, we'll pretend that it's an ideal and stable magnetic material, where Chi-M is constant, and even equal to a nice round number, like 200,000. Here are typical values for relative permeabilities of different materials. Most of them are very nearly equal to 1. Iron, which is a strongly magnetic material, has a very large value. Here are typical values for susceptibilities for the same materials, most of which are very close to 0, with only iron and cobalt having large values. Here are the values for the permeabilities of these same materials, most of which are nearly equal to the permeability of free space. Here are some values of these quantities as found in a typical inductor. The external H magnetic field, H in an inductor, is only dependent on the current through it and the density of the wires that coil around it, also called the number of turns per unit length. Notice too that all of these values are independent of the value of the inductance of the inductor. Here are the values of the other H quantities, called HT and M. Here are the corresponding values of the magnetic B fields. Here is the external magnetic B field. And here is a quick check of the values to see whether they are correct or not.